Hello, Professor.
Hello.
I had a question from last class.
Yes.
So I know we said like the increments are independent. So like, like you put the example B8 minus B7 is independent of B7 minus B6.
Yes.
But when we were doing, the Riemann integrals at the very end with etos,
Yeah.
yeah. Why can you say that the Bn times the Bn plus 1 or Btn times the Btn plus 1 minus Btn is independent?
Oh, we did not. I hope we didn't say that.
Oh, so then how did you know that the expectation of those multiplied together was 0?
So we should have. There were two expressions. Right? We had one where we had Tn plus 1 times
Yeah.
Btn plus 1 minus Btn.
And that one was the Tn.
And the other one was Btn times Btn plus 1 minus Btn.
Yes, that one.
So which one is it you're asking about?
So the second one in class, you were able to split the expectation.
Yes, right? Because this thing here, this is independent of Btn, for example, minus Bt0.
Okay.
Right, because we're looking at, if I'm looking at this interval, and I'm looking at this interval. So I'm looking at how the Brownian motion has changed from Tn to Tn plus 1. Here,
Right.
to change Btn plus 1 minus Btn. And here, for example, if this is my 0, then I'll look at how the Brownian motion has changed from time 0 to time Tn, and this will be Btn minus B0, right, which is Btn.
Oh.
It's very independent.
Okay. Okay. I get it now. I get it. Because I was like looking at the example you gave on the very first day when you said, B8 is not independent of like B8 minus B7. And so I was looking at it like that. And so I was very confused. I didn't think.
That's what you get up here.
Right.
That's exactly what happens up here.
And that's when you have to do like the trick where you add it, you like subtract and then add.
Yeah.
Okay.
Yep. Yeah, right. So you can, for example, write this thing. I write that in red, right? So I can write this quantity. I can write as Btn plus 1 minus Btn plus Btn.
Yes.
Right. So the first part, these two multiplied together, this is going to give me Tn plus 1 minus Tn.
Right.
And the second part, I use exactly the same as what I did below. This is independent, so that's going to be 0.
Right.
So this expectation here is just going to be that.
Okay. That makes sense. That makes a lot more sense. I understand why that's equal. That second one is equal to 0 now. But that leads me to another question from the homework. I don't know if you have time to answer it right now.
Yeah, sure.
Okay, so for question 4, when we're proving it's a Brownian motion, I know we have to prove that its distribution is normal with expectation 0 and variance t minus s, but I'm getting s minus t. Like I'm getting the opposite of t minus s.
Okay, is this question?
Yeah.
Yeah. So if we do, so if you look at, so t bigger than s, I'll have b hat t minus b hat s.
Yeah.
This is equal to bt plus t minus bt. Minus bt plus s minus bt.
Oh, wait. I think I understand. Okay. Got it. I was putting a minus. I put t minus t and t minus s. That is why I was getting the opposite.
Okay.
I got it. Thank you. I appreciate it.
Okay.
Professor.
Yeah.
I tried doing the homework for this week, but number 2, I like had no clue how to do it. Like, is there any like intuition?
Let me try to bring it up.
Oh no, yeah, number 2. Oh wait, no. Oh no, sorry. Question 1, part 2.
Oh, this one.
Yeah.
Yeah. Do you have any suggestions on your own?
No, I tried for a while. I didn't have anything. I thought about using Chevyshev's, but I didn't really know where to go with it.
Well, keep in mind, if you use Chebyshev, you're going to get an inequality.
Yeah.
So we're asking for an equality here. Well, you look at that there are 2 random variables in play here, right? bt and b2t, right? So you can take t to be 1, maybe just to get started.
Yes.
So then you're interested in p of b1 is positive and b2 is negative. So what would happen if, so b1 and b2 are the independent?
Yeah, I would say yeah, because they're both defined as Brownian motions.
Well, there's only one Brownian motion here.
Oh, okay, then no.
So if they're not independent, what could you do?
I'm not. Could you like minus 1 then add 1 and like in the inside?
Yeah. So let's do b1 bigger than 0 and b2 minus b1 it's less than minus b1. So now you'll have that this quantity here is independent of that thing. So then what could we do?
From here on, can you just split it then and then just proceed from there?
How would you split it?
Just like right where the comma is, because it's like that's like it's an n, so it would just be multiplied.
Well, be careful. There's a b1 over here.
Oh,
right. These two are not independent of each other.
yeah.
So these, I mean, this is not the same. This is not the same as these two, right? Because these are not independent.
Yeah.
But what comes to mind when you see this?
Well, I think I would just split the probability of b1 greater than 0 and then take the other one and leave the inequality, and then I don't know where I'd go from here.
Okay, so it's not far away from a calculation that we've seen before, right? So we could for example use iterated expectations, right? So this here is the same as the expectation of an indicator, right, for b
Yeah.
being positive, an indicator for b2 minus b1 less than minus b1. Right, so we could use conditional expectation. So we could use that the expectation of a conditional expectation, for example, and we could condition on something here. And we could, for example, condition on b1.
Okay, and then we can use the lemma, and then so some of them get pulled out.
Yep. So we could pull this thing out. And now what about the last part?
Well,
We have b2 minus b1. How does that relate to f1?
It's not yeah, I don't know, because the b2 wouldn't be measurable under f1.
No, it's not going to be measurable. Well, how does this thing relate to f1?
It's independent.
It's independent. And how is b1 related to f1?
It's measurable.
Okay, so what do you want to use here?
We can use the independent limit again.
We have not used it yet.
Well, yeah, we pulled it out. But right here we could, yeah.
Right, so this would become the expectation of b2 minus b1 less than, and then you put in a dummy here. And now we replace the dummy with b1. Now we have something.
Oh yeah, I think I see where it's going now.
Yep.
Okay, thank you.
Here that x is equal to minus b1 or b1. Okay.
Well, yeah. Right. Okay, are there more questions before we get started? Are there any other questions or comments, or? Okay, then let me just blow my nose. So let's get started. See, so we are working ourselves into continuous time finance, and at this point we have an object which we call a Brownian motion. Some people call it the Wiener process. Right, so this is a collection of random variables that satisfy some properties. And most prominently, we'll know that B is a martingale. And we also know that the quadratic variation of the time t is simply just t. Right, so this is just a quadratic variation. So now our goal is, so the next big goal is to define and study the E2 integral.
楼道里是你说话吗？
I'm sorry, can you say that again? Was there a question?
No, I think that was just background noise.
Yeah, just back.
Someone's mic.
Okay, so the next goal is to define the E2 integral. And so we're going to know the E2 integral. This is going to look like this. An integral from 0 to t, then there'll be an integrand, delta, and then there'll be this symbol here, right? And this is a stochastic process, just like B up here is a stochastic process. So we want to define this object here. And we want to study its properties. Right, so we could be interested in, is it a martingale? Rohan is asking, is U a subscript of delta? Yes, it is. This is delta sub U, just like it's B sub U. For a class of processes, delta U. So examples could be, we would have a delta U, could be, it could be like an exponential of U. It could be that delta U would be Brownian motion. It could be that delta U would be e to the Brownian motion. Could be something more complicated. Could be that delta U is like a running max, like what you have in homework of, say, Brownian motion. It could be any one of these and many other things too. So this is the goal to do. And so it's an integral. One should not mistake this integral with a Riemann integral. This is not the case. This is dBu. So this is quite different. I should say this is going to be very different. This is very different from, say, an integral from 0 to t of delta U du. So for example, we shall see that an integral from 0 to t of bu, so now I'm looking at the second example here, we shall see that this integral here, indexed by time, this is a martingale, whereas if I compute the conditional expectation, say from 0 to t, whereas for t bigger than s, or bigger than 0, if I compute the conditional expectation of, what will it be up here? It will be bu du given fs. I'm going to get something quite different. So here, what I will do is I'll write, so to compute this, what I can do is I can write this as, what I can do is I can write this here as an integral from 0 to s of bu du plus, and then an integral from s to t of bu du given fs. So here I'm integrating the Brownian path up to time s. This is going to be measurable with respect to fs. I'll simply just have that the first part is this guy. And now for the second part, I can pull the expectation inside the conditional expectation. So here I'll get EBU given fs du. And then, so we will have the first term. We will have the first term and we'll have the second term. But now we'll use that B is a martingale. So when I condition on a future value, like U here is between S and T, particularly is bigger than S, conditioning on BU, or conditioning BU on FS, I'll just get that this here is the integral of BS du. And then finally, we can work out what the second integral is. This will be T minus S BS. Right, so this is not a martingale, because if this were to be a martingale, this quantity here should not be there. This here is not 0. Right, so I'm trying to stress here that this object that we're about to introduce, it should be in no possible way treated as a regular integral. Right, so we have not seen that this is indeed a martingale. However, this calculation here we can follow it, so we can see that it's not going to give me a martingale property of this object up here. We good so far? So how do we define integrals? Well, we define integrals, the spirit, the way to define it is similar to what we did for the Lebesgue integral. So we start simple. We start with simple processes, also called elementary. And then extend to general. These are the deltas, so we do general deltas. Okay, so we need to define what is an elementary process. Okay, so we say that this object is a simple process if I can write it, if I can write delta u, if I can write delta u, if I look at u's, between, say, 2 time points, so say t n plus 1 and tn, and so we have to make a decision. We need to either, we can't have it close both ends. We need to keep one of them open and the other one closed. good news is it doesn't matter for what we're doing, but maybe we want to be consistent with what the textbook does. So we just double check what Steve he decided on. There's an option here. You can choose whichever one you want. And we just make sure I get the right thing. So he calls them simple integrants, 1 to the 5. Just want to make sure I get the inequalities like he does. Yeah, so he keeps it close to the left and open to the right. So I'm going to follow Steve. I'm going to follow Steve here and say, we're keeping it close to the left and open to the right. So if delta U is equal to delta Tn for all U between T and Tn, where T0 is less than T1, it's less than Tn, less than infinity, for some n in the natural numbers. Right, so what it means is that I have a simple process if it's piecewise constant, and the value that it takes on one of these pieces is the same as the value it has at the left endpoint. So maybe we're trying to make the picture that Steve had in the textbook. So we will look at intervals Tn plus 1. So in here, the value will be frozen to the right, and it will stay flat here, and then it will stay open there. And then at the next time point, it will be something else. Tn plus 2, so stay open. It'll go like this. So as an example, we could look at you pick points, say 0 is equal to T0, less than T1, up to say some Tn, and then you set delta U simply to be Btn for U in the interval Tn plus 1. So if I have one of these simple guys, how should I define the integral? So for delta simple, we define the integral from 0 to t delta u dvu. How should we define it? Well, again, let's say that t lives between Tn and Tn plus 1. So what we'll have here is we'll have the value, we'll have a delta T0, and then we will integrate from T0 to T1 dB. That will be BT1 minus BT0 plus, then on the next interval, we will have delta T1 times, so now we integrate from T1 up to T2, so we will multiply onto BT2 minus BT1, and we'll keep doing this until the last interval. There we will have delta Tn, and then we'll have to integrate up to Bt minus Btn. So that's the integral for the simple processes.
Why is it not btn plus 1?
There,
Yeah.
because that t I'm looking at, that t up here, it could sit somewhere in this interval. So if you have the picture, so I'm starting out, say I'm starting out here at t0. So I have t1, t2, right, and then I have my tn, and I have my tn plus 1. And in between there somewhere, I'll have my t.
Okay.
Right, so I don't know that my t is sitting all the way to the end. It could also sit all the way in the beginning. You know, there'll be something in between here. So that's why it doesn't go all the way here. I mean, ultimately, what's going to happen is that we're going to pass these distances here. We're going to pass them to 0, right? So we're going to increase the number of time points, and then this is really not going to matter much. This little piece here is not going to matter much. But for now, I want this thing to be a stochastic process so that it's going to be defined for all t. Right? It's going to be defined for all t, so t is going to sit in one of these many intervals, and here I just denoted that interval by tn to tn plus 1. Does it make sense?
Yep, thank you.
So at least so we're at this point here. We're also at this point when we did the Lebesgue integral. We're at this point where we have it defined for these elementary ones, and then we want to try to extend it. I'm not sure we're going to do the extension tonight. There are plenty of things to play with because this is new and it's quite different than what we've seen before. Let's try to look at some properties. Of the textbook calls this IT, this integral here. When delta is simple. So what kind of properties could we have? So there are, we already alluded to the martingale property. So maybe we could start by proving. So one of the properties it has is that it's actually a martingale. IT is a martingale. Okay, so how would one go about proving that? Well, again, let's look at the timeline. I'm going to be interested in picking out. So I'll have a t bigger than s, bigger than 0, and I'll put my s in a bin, tn plus 1. So I'll put my s in here, and then out here somewhere is where I'll have my t. So I'll have my tm and my tm plus 1. Say this is how it looks like. Then I'm interested in computing the conditional expectation of IT given fs. And so how do we do it? Well, we can start by writing out the integral. So we will use the formula we had up here. We'll use the formula we had up here. So we will go with all these terms all the way up to the last one. The last one will be delta tm BT minus BTM. So let's start by writing that. Delta T0 BT1 minus BT0 plus a bunch of terms. So probably something interesting is going to happen here. So let me single that out. Delta Tn times delta T BTN plus 1 minus BTN plus more terms. And then the last one will be delta Tm BT minus BTM given Fs. So let's see what we get here. Okay, what about the first term? Conditional expectation of this object here, given that one, what do we get there? The first term, given that one. Well, S sits between Tn and Tan plus 1. Okay, so this here involves something that looks over here at T1, and then a bunch of points over Tn.
So it's measurable.
So it's measurable, so he just goes outside, happy as he is. And then a bunch of terms. So here we get something that's interesting. What about this term? Now S sits between Tn and Tn plus 1. So delta Tn, well, Tn comes before. So that one goes outside. And then here, Tn plus 1, this comes later. So we keep him. Put the expectation. So we have Btn plus 1 minus Btn given Fs. Plus all the other terms that are going to be inside there. And plus this delta Tm Bt minus Btm given Fs. Okay, so what do we have left? What about this part here? What does he become?
Here is martingale.
Yeah. So here S sits right in between these two guys. So B is a martingale. We're going to get to this here is Bs minus Btn.
Why?
Right, so Tn is less than S. Right, so this term here is already measurable. Tn plus 1 is bigger than S.
Yes.
So what is the conditional expectation of a Brownian motion at a later time given an earlier time?
The difference?
So if I take the Brownian motion, this is at a later time, given an earlier time, we just get the Brownian motion at the earlier time.
Previous time?
Yeah.
Wait, what do we get? Sorry.
I thought Brandon motion at the previous time.
Yep.
Oh, okay.
The Martin. So when I combine all the first terms here, there is a bunch of them, all these terms here, what do they combine into? Well, this is going to be exactly the Ito integral up to time what? Well, up to time S. So if I want this thing to be a martingale, everything that's over here better be what?
0.
0, right? And so, Ibrahim, can you argue why this is going to be 0?
Give me a second, sir.
So we need all the remaining expectations to net to 0. Okay, so we can get that to 1.
I have a quick question. Are those remaining expectations independent of the FS or?
Yeah. Be careful here. It is that it's pretty close, but you have to come up with an argument for why is this independent of FS? Maybe it's obvious to you, but
Isn't it FS? I mean, yeah, S is at a previous time point.
yeah. So if I work on the last one, so let's consider the last one. Right, so remember, S here sits far away to the left. Right, so S is much less than TF. How would we argue that this is equal to 0? Well, we could argue by using iterated expectations. So what we want to condition on, we need to figure that out. And when I'm done, I'm going to condition on FS. What should we condition on here? F something.
T.
M. Oh, T.
TM. Right, so now I can use that this thing here is measurable. So he goes outside. And then I can use that this random variable. How does that relate to TM?
Independent.
In case anybody wonders, is this stuff that we've seen like a million times up to this point? Have you seen this before? This line of argument? It's what we've been doing all semester, right? It's the same thing that we're doing over and over and over. We're just rephrasing it in terms of Brownian motion now instead of what we were doing with the binomial model and all these other things. It's the same few steps that we do over and over and over. And it leads to all these conclusions. What is this expectation?
0.
Yes. And likewise for the other terms. So it's a martingale. This is this fantastic property. So some books, not many, but some books call IT for a martingale transform. And basically what's going on here is this way, like what is the key thing that makes this object a martingale? So you go back and you look at what's the property that we're using. Like we're definitely using something about BT being a martingale. Like that was this calculation here. We used that this was a martingale. Right, you gave me BS here, and then same thing over here. I can. So when is this going to work? Well, if I know that BT here, if I know that BT would be a martingale, then I can pull this thing outside the conditional expectation of BT would then be BTM, and then you get BTM minus BTM, and you get a 0. So I don't really need this independence of increments. It's okay if I just have a martingale. Rohan is asking something. yeah, this has mean 0. Brownian increments mean 0, variance t minus tm. But what I'm saying is you actually don't really need to use the independence here. So if only B was a martingale, that would be sufficient because E of BT minus BTM given FTM. If B was only a martingale, we would have the delta be 0. Here we're using that we're using more properties. We're using that the increments are independent. So that's the martingale transform, the Ito integral for simple or elementary processes. What else could we come up with? We could come up with, this was one property. Let's do another one. This one here is so famous that it has a name. It's called the Ito isometry. Has anybody heard the word isometry before?
It preserves distance of 2 points when you map 2 points into.
So you guys have worked with this before. So there is something here that is familiar. Okay, so let's talk about the Ito isometry, right? We have our M, we have our so because IT is a martingale, we know that martingales have constant expectations. So the expectation of the Ito integral is pinned down to be the same thing as the initial value, which is a 0. But the Ito isometry gets at, this is the first moment, the Ito isometry gets at the second moment. The Ito isometry says there is a way to calculate the expectation of IT squared. Right, so this here is the IT is just a short way of writing this integral. There is a way to calculate this mess here. And the way to calculate this mess here, so this here has no information. This is just I plug in what IT is. Here's the Ito isometry. It says you calculate this here just as an integral from 0 to t. And then this square up here, it travels inside here. And then this dB here, this square also somehow in some sense travels inside here, and we put in the quadratic variation of Brownian motion. Remember, the quadratic variation of Brownian motion is something we already talked about. Quadratic variation of Brownian motion was time. So you get du here. And this is the first time we're seeing a connection. We're seeing a connection between the stochastic integral and the standard Riemann integral. This here is just, this one here is the Riemann integral. It says that if you want to compute the second moment of the Ito integral, you can do that by computing an expectation of an integral with respect to the Lebesgue measure. So there is a connection between the two worlds. we will see that connection being exploited. We will ourselves, we're going to be using this, that there is a connection between these stochastic integrals and the Riemann integrals quite a bit in this class later on. So how would one go about seeing? How would one go about seeing something like that the isometry is true? So let's do. And I think I'm just gonna focus on t being just a tn here, so we don't have to worry about. I don't have to worry about. I don't have to worry about splitting in between tn and tn plus 1. I have shown you now how to do that. Let's just look at a simpler special case here. And in this case, I can look at ITN squared, and I can work out what this is. So this would be a sum from, say, k running through 0 to the last one will probably be n minus 1, yeah. And then we'll have our delta tk b tk plus 1 minus b tk. You have to square it. So let's see, there'll be, what kind of terms will we find on the right-hand side? We are squaring a sum, right? So we will have different terms. So there'll be two kinds, there'll be two types of terms. On one hand, you will find terms like delta tk squared, and then this increment btk plus 1 minus btk. You'll have terms like that. And the other kind you'll have will be the off-diagonal terms, tk, and then delta maybe tj times btk plus 1 minus btk. And then it'll be btj plus 1 minus btj. So we'll find these kind of terms. And now we're interested in computing the expectation of them. So I'm interested in computing the expectation, right? I want to compute the expectation of this E2 integral squared. So I need to compute the expectation of this stuff here. Okay, so I need to compute the expectation of these terms here individually and then sum them up. So what will I get if I compute the expectation of the first kind? So I'll look at E delta tk squared btk plus 1 minus btk squared. How would I compute that one? Well, we've done it before. When in doubt, use iterated expectations. So let's plug in another conditional expectation in here. What should we condition on? What should we condition on here? Should be something with f.
tk plus 1.
Tk plus 1, then everything inside is going to be measurable.
TK.
Tk. And then what would we get? Well, this guy here is not going to be measurable. He is going to run outside. And what about the last part? Well, how is this random variable related to this one? Very similar to what we had before. This is going to be independent of what you have here. So we just have the unconditional expectation. btk plus 1 minus btk, everything squared. This was exactly what we had up here, except there's no square here, right? There was no square here. We just get the expectation, no square. So now there's a square, and what does the unit guy become?
The variance,
Yeah, which is equal to
tk plus 1 minus tk.
Yes. Right, so I combine everything, I get that this is the expectation of delta tk squared times tk plus 1 minus tk. And if I really want to, it might look a little bit silly, but I could write this here as an integral from tk to tk plus 1 of this e delta tk squared du. There's no u dependence here, so he can go outside the Riemann integral. I'm integrating with respect to du from tk to tk plus 1. I'll just get the length of the integral I have up there. So that was one guy. That was the first kind. That was these terms. Okay, so we also compute the expectation of these ones. So now k and j are not the same. So we need to settle on which one is biggest. Okay, let's consider the case k. Let's consider the case that tk is bigger than tj. Now what do we get? What is this expectation? Delta tk delta tj, and then the Brownian increments. What do we do? How do we attack this one?
Do we do the same thing? Iterated expectation?
Just let me know, Ibrahim, when you get tired of seeing me do this. And what do you want to condition on?
F T J.
TJ, small one.
Yes.
Very good. Maybe we should take a bigger than that. Maybe I'll write it like this. If, let's see, what do we get? Yeah, if tj plus 1, I think is the one we want. We can even go further. We can go all the way up to maybe tk. Yeah, let's put a k here. Let's do tk. Because then I can pull out this part. I can pull out these two parts. Delta tk, delta tj, btj plus 1 minus btj. And what am I left with is tk plus 1 minus btk given ftk. What do I get?
Yeah, unconditional expectation.
Yeah, and what is that equal to?
Will be btk minus
BTK minus 1?
Oh, there's no minus 1 here. We only have btk plus 1 minus btk. This here is going to become the expectation of btk plus 1 minus btk. What is this expectation?
0, right?
Yes.
0.
So what's the condition? So then everything goes to 0, right?
Yeah.
Okay, so now we got these diagonal terms. We figured out what that expectation is, and the off-diagonal terms, they all have expectation 0. So we are now one step closer to saying that the expectation of ITN squared, this is going to be the sum of from k equal to, what was it, 0 to n minus 1, expectation of delta tk squared times btk plus 1 minus btk squared. And those are the ones we had computed. Those are the ones we had computed right here. So I don't have the sum from tk, from, what was it, k equal to 0 to n minus 1. And then these integrals, tk plus 1, delta tk squared, expectation, du. But of course now I'm varying k here from 0 to n minus 1. I can write this here as an integral from 0 to tn of e delta t k squared du. I have to be careful here. I should put here, when I am on this interval, I have to be careful with this index down here, right? Because there's no k on the left-hand side. I know that delta here is simple. So on the interval tk to tk plus 1, I'm constant. I'm constant, and I know here, so what am I using? This quantity here. I could write this as an integral from tk plus 1. But when u varies between tk and tk plus 1, I can write here delta u squared du. Right, and this is because delta u is equal to delta tk for u between tk and tk plus 1. Right, so here should put a u. And that was the e to the symmetry, right? I can pull the expectation back outside if I so decide.
I have a quick question. So this k is like, even though it's changing, delta u squared, delta u is still equal to tk, delta tk, even as k changes from like,
No, so on this interval here from tk to tk plus 1, delta u is equal to the left endpoint. So,
right.
so I can write this integral here as what I have here.
Right, but the left endpoint is like your k could be like 0, it could be 1, could
Yes,
be 2, but it's all delta u when you simplify it.
yeah, the u, so this is why I don't want to write tk here, right? Because there's no, I don't have any k on the left-hand side of my equation, so I cannot write anything on the right-hand side in terms of a k. That won't work. I cannot write this tk I had written here. I should just, up here in the previous slide, I should have finished the slide here by doing that calculation. This expression here can be written as tk to tk plus 1 of the expectation of delta u squared du. Right, because delta u is always equal to delta tk when you're on the interval tk to tk plus 1.
Okay.
Right. So if you have it here, just copy paste it into here, right? And then I'm using it, I'm integrating over this disjoint interval. So I'll get the integral from 0 to tn. There should be no tk here, it should be delta u. So that's the e to the symmetry.
Wait, why is it called an isometry? What is it preserving?
Why is it called an isometry? Yeah, so why use the word isometry? Okay, so if you have a space, if you have a space, and we actually have a space, yeah, I don't know, maybe we should just keep it abstract here. I have a space over here. This is, we call these for x's. And over here, I'll have my f of x's. Right, so I'll have a map that'll go between these two, and I'll call it for f. So when is f an isometry? Well, I'll be interested in measuring the length of x. And I'll be interested in measuring the length of f of x. Right, so here, this is in some space. Call it capital X, and maybe we'll call this thing here for capital Y. So when will I call f an isometry? I'll call it an isometry if f preserves length. So we say f is an isometry if the length of x over in the domain is the same thing as the length of x of f of x over in the codomain for any x in x. So what we're measuring here is, so in our case, it's a bit more messy, because what I'm measuring over here is my object is this delta. The thing that I map with is my I operator. And so what comes out over here is this integral. We just call it I. What comes out over here is this IT. So here I'm looking at the integrand, and here I'm looking at the E2 integral. So I need a good norm. What kind of a norm should I put on my I? Well, the norm of my IT. The norm of my IT. It's just going to be the L2 norm. So the norm squared is just going to be the expectation of IT squared. And then what kind of a norm should I put on this one over here? Well, the thing I'm going to put on a norm over here is the norm of my delta. Right, so this is a definition. The norm squared, I can move the square to the other side if you want to do that. This one here is what? This is going to be, again, an expectation, but it's going to be an integral from 0 to t of delta u squared du, and then the square root. So this is why it's called an isometry. These two quantities, they are exactly the same.
So the map is I of t.
It's always a little tricky. I don't like to have, I will not call the map for f of x. Right here is just I. Just like here, I didn't write f of x here, right? The elements that I get out in the in the image, those are called for f of x, and so here I'll call it for I of t. like normally you'll not say that a function, there's no meaning to saying the function f of x. It should be the function f, because you can plug in anything you want. It doesn't have to be t. It can be any.
Oh, so I mean, I meant like, was the little? Is it just I there?
Just I, yeah.
Oh, I thought the little.
No, because I wrote IT here and I changed.
Okay, yeah, I got you.
I don't want to call this for IT, because IT is the thing that comes out over in the
Right, it's when you evaluate the function.
Yes, that's right. Yeah. Just as up here, I will not call my map for f of x, I will call my map for f. And then f of x is what I get out in the coding. So that's why it's called an isometry. There are some questions in the chat. Yeah, so isomorphic, then you need to have an isometry. So we have an isometry here, yeah. Why is that our metric? Well, I mean, it doesn't have to be, but you can just see here that if I put these as my, and these are not metrics, right? These are norms. This is a norm. And so what we're playing with here, we're working with LP spaces. More specifically, we're working with L2 spaces. So then if I have a random variable for x, we define, we can, I should not say why it is, I mean, we can, there are many other ways to do it. We can define the norm of x, and this will typically be denoted by the 2 norm. The 2 norm squared is defined to be the expectation of x squared. Just like the 1 norm will be defined to be the expectation of x's absolute value. More generally, the p norm to the power p, this is the expectation of x to the power p. For p bigger than or equal to 1. And these are norms. These are norms on LP of omega. And so if you want to get a metric you can get by saying, well, I want to measure the distance between x and y. And you measure that simply by looking at the, if I want to have the p metric, I'll look at the difference in the p norm. So just some things to note. When p, for example, is between 0 and 1, LP is not a norm space, but there is a metric. And so there's a sharp, being a norm space is much better. It's much finer to be a norm space than it is to be a metric space. This is D. This is a D. DP. This stands for distance. So if you're not familiar with this material, this is really not something that we're going to be using. But if you're taking a course in real analysis, I know some of you are. You're probably working with a you're probably going to be working with these norms and metrics. No, LP is not. So this is not. This is a space. This is that space from your homework. LP spaces are those functions that are p integral.
Is it like a, what kind of space? Is it like a, yeah, vector space or like a topological space? Or
But it's much more than a topological space. It's much more, right? It has a distance. And if you have p equal to 1, then it's a norm space.
is norm space the same thing as, is that related to inner product?
No,
No.
that only works for this guy.
Okay, okay.
There's a food chain here, right? There is a food chain. First, you have a Hilbert space, right? And then that's the L2. Then you move down, then you get a Banach space. So this is like your LP, p bigger than 1. And then you can put into a metric space. And then you can also do p bigger than p bigger than p bigger than or equal to 0. Right, so when all the way down here, there's going to be some topological space. Yeah, I mean, in our case, right, these functions we're talking about, these are measurable functions, the random variables. And we cannot define this expectation here unless you have measurability. So we cannot get away from measurability. So we're always dealing with measurable functions. I should also say over here, there is, but this is taking us way off course now. Like in this food chain here, there's more structure to it than just calling it like a Hilbert and a Banach space. You also need completeness to get this thing to work, right? So you need to know that if I have you also need completeness. To get, for example, a Banach space. So if I take xn minus xm, right, and I want this to go to 0, then I want to make sure that the x's actually have a limit, that is implied that xn converges in this norm. So because these sequences, they have limit points. Right, but you only have the Hilbert structure. I forget who asked about the that structure. Right, this thing here, this is equal to the inner product between x and x. For L1 and for LP in general, there's no inner product. Only L2 for the LP spaces is a Hilbert space. Okay, this took us way away from the last property I want to mention is the credit gradation property. We also need that one. So the last one, this was property 1, 2, and the last one is if I want to look at the credit gradation. So the credit gradation of I that's going to be equal to the integral from 0 to t. Right, so delta u squared, and then t, and then the credit gradation of b. So this is going to be equal to the integral from 0 to t of delta u du. So another way to write the E2 isometry is to say that the expectation of IT squared is equal to the expectation of the quadratic variation of IT. Okay, so next time we're out of time, but next time we're gonna extend IT from simple to general deltas. And the general deltas that we're going to be looking at, so our class of deltas, our class is given by, so the first property that you have to satisfy is first thing is that delta u is fu measurable. And the second property is that when I compute the expectation of the integral from 0 to t of delta u squared, du, I'm finite. And so what we can see here, so this includes delta u being bu, delta u being e to the bu, delta u being, say, this max of bs up to u. What were the other ones we had in the beginning? We had bu, ebu, we had the max, and then we had, so here we also have e of u. Also put that one in there. Like these guys here, none of these is simple. So the definition that we just went through, that would not include any one of these four because they're not piecewise constant. And so if you want to be able to include like Brownian motion, exponential Brownian motion and such processes, we have to go beyond what we just did because these are not piecewise constant. Because there's some work to be done on how to extend this integral. And the way that it's going to be extended is using the isometry. So this is how Ito originally did the extension. But we're out of time, so I think this is a good place to call it quits for tonight. Are there any questions before we wrap up? My camera broke on my computer, so I can't show you my picture. I can show you like upside down, but it doesn't really work so well. Are there any questions or comments? I know this is gonna, we're introducing yet more material. So I know for some of you this is a bit of a challenge, but I think we can spend the last month here trying to do some continuous time finance, and to do that we really need this stochastic integral with respect to Brownian motion. Are there any questions or comments?
Professor, do you mind pushing the homework to Sunday?
No, not at all. Not at all. That's fine.
Okay, thank you very much.
No problem. questions or comments? Okay, then I will see you guys on Thursday. So once again, on Thursday morning. So there's been a change of office hours, right? So we have, because the other class I was teaching, we've broken off. Now we do continuous time, and they started doing American options. So there are separate office hours now for the two classes, and our class 45, we have office hours on Thursday and Friday mornings at 9 o'clock. Okay, so if you have questions, you're more than welcome to show up there and ask questions. Otherwise, have a good night, guys, and I'll see you on Thursday.